Okay. Everyone, hello everyone. Welcome to the mechanics materials. In this video, okay, we just follow the previous video. In previous video, I think I talked about the Cartesian vectors. Okay, that means representing or express your vector by Cartesian coordinate. In previous video, we introduced the 2D case, 2D system. Yeah, but now I just want to go a little more advanced because it's for introduce the Cartesian vector in 3D space. Okay, yeah, just in 3D space we just add one more component, right? Because in 2D case, in 2D system we only have two components. Okay, in 2D system we only have two components. Okay, let me write. Okay, and my pen. In 2D system, we only have two components, AX and AY. But now in 3D case, we have three components, AX, AY, and AZ. Okay, and IJK is the unit vector for x-axis, y-axis, and z-axis. Okay, that's the convention. IJK, I for x, J for y, and K for z. And the component of sorry, and the magnitude of the vector A is just the sum of the components square x squared plus ay squared plus az squared, and sum of them and take a square root as the magnitude of the 3D vectors. Okay, and here we introduce called Cartesian unit vectors. Okay, so just when I say a vector is equal to magnitude, okay, magnitude and times the directions. Okay, it's very important concept. Vector, you have magnitude and direction. And actually, it's really equal to magnitude times the direction. And if you express in mathematics, you say it's just like this. Okay, a vector A equal to the magnitude of A vector and times the unit vector of the A vectors. Okay, and this is unit vector. Okay, so let's say so this is called unit vectors. Okay, the name another name is called the direction is unit vectors, and it give you the direction. Give the direction. And this magnitude give you the magnitude, and this unit vector give you direction, and its magnitude always one. Okay, its magnitude always one. Okay, the unit vectors in the unit vector, the magnitude always equal to one. Okay, unit vector. Okay, its magnitude always equal to one. Okay, that's the definition. In the unit vector, the length or magnitude of unit vector is always equal to one. Okay. 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 So what? And then okay. And then what's the inside the unit vector? Actually, it's very simple. Yeah. You just follow this definition. Okay. Yeah. Because yeah, just follow this definition because, like I say, vector equal to magnitude times direction. So I can write I can write a vector in this way. I can write a vector this way. I just factor this magnitude out, ax squared plus ay squared, az squared, and then I put and then sorry, it looks like I don't. There's no much space here. Sorry. Maybe I just add a space. Sorry, let me just add the space quick. Okay, let me just add a space quickly. Okay, okay, okay. So I have AX. I representing my vector in 3D space. Okay, in 3D coordination. A 3D space with 3D Cartesian vector. Okay, I can factor this out because the magnitude is just a constant. Okay, times, okay, here, ax squared plus ay squared plus az squared. Okay, I And okay, let me write here. Okay, plus j and plus k. Okay, I just factor this the magnitude out. Okay, and nothing change. Okay. Y A Z. Okay, I just factor this magnitude out. Okay, and then inside we will become ax divided by magnitude I plus ay divided by magnitude j and az divided by magnitude times k. Okay, so vector equal to magnitude times the direction. So this is your direction. And this direction is just is equal to is your unit vector. This is direction, so it's also a unit vector. Okay. So how to calculate the unit vector? Actually, it's very simple. Suppose you are given you are given a vectors, and how to calculate the unit vector? Okay. So first of all, just calculate its norm or its magnitude. Okay. And your unit vector just equal to x component divided by magnitude plus I plus y component divided by magnitude j plus z component divided by magnitude and k. So actually, this is the way you how this, this, should, this is the way to calculate a unit vector. Okay, and this unit vector, sometimes you will hear another name is called because these three terms. Okay, these three terms sometimes you will see this name. The first term is called cosine alpha. The second term is called cosine beta, and the third term is called cosine gamma. And this we will see another name called directional cosine. Directional cosine. Okay. Okay, and alpha, beta, gamma, these are three angles. Okay, the alpha is the angle between the vector A to x axis. Okay, so let me see. Maybe I should change this to the hit here. Yeah, okay. Let me just okay, temporary close this off. Okay, so where is alpha, beta, gamma? Alpha angle is the angle between the vector A and x-axis. Okay, and beta is angle between the vector A and y-axis. And gamma is the angle between the vector A and the z-axis. It's called alpha, beta, gamma. Okay, it's a convention. Alpha to x for x-axis, beta is for y-axis, and gamma is for z-axis. This for convention. Okay, we need to follow this convention because yeah, there's a convention we can make life easier. Okay, so just follow this convention. Okay, alpha for x, beta for y, and gamma for z. Okay, so and okay, let's back to this. Okay, that's the alpha, beta, and gamma. And cosine alpha, cosine beta, cosine gamma is called directional cosine. Okay, this okay. Let's just give you the direction information. Okay, but it's just component of your unit vector. That's it. Okay, just yeah, you see this cosine alpha, cosine beta, cosine gamma. It's just the component in your unit vector. That's it. Okay. That's not really nothing very special, right? Okay. Okay, so let's introduce you the vector in 3D space and introduce and show you what is the unit vector. Okay, how to calculate unit vector. Okay, so let's in this video we just quickly show a very simple example. Okay, a simple example here. Example 2.7. Okay, and example 2.7. Let me erase this. Okay, I will write this. Okay, the first is a very simple one. It's just example 2.7 from a textbook. Okay, it gives you the two force vector, and you want to determine the coordinate and direction of resultant force acting on the ring. And this ring has two force, F1, F2. Okay, right now there's some answers on the PowerPoint, but unfortunately this is wrong. Okay, unfortunately this is wrong. Okay. Okay, let's start with this very simple exercise. Okay, it is the 3D problem. Okay, it give you F1, F2. Okay, we want to find the resultant force. Okay, resultant force means 合力. Okay, resultant force. So let's write down the F1 and F2. And it also express the F1, F2 by the Cartesian vectors. Okay, Cartesian vector. So it first of all, F1 is 60J plus 80K. Okay, and he doesn't show you any information of the I component. That means I is zero. Okay, so it's zero I plus 6J plus 80K. And F2 is 50I minus 100J and plus 100K. Okay. And okay, so so what's the resulting force? Okay, resulting force. Okay, if you use vector, the resulting force is just the F1 plus F2. Okay, F1 plus F2. And in the previous video, I say okay, if you use the Cartesian coordinate to express your vectors, and vector addition and subtraction is very easy. Just a component added by component or component subtract a component, right? Okay, so that's why express your vector by Cartesian coordinate is help you in doing the calculations. Okay, that will make life much easier. Okay, so F1, F2, okay, let's just say it's I, J, and K. Okay, we component add by component. So X component, X add X component. Okay, and Y component add the Y component. And Z component, yeah, Z component add the Z component. Okay, then. So after all, you will have 50I minus 40J plus 180K. Okay, so that's the resulting force vector. But the problem wants you find the magnitude and coordinate direction angle. Okay, that's just the angle. That's just the angle of your vector between x axis, y axis, and z axis, alpha, beta, gamma. You want to find alpha, beta, gamma. Okay, find alpha, beta, gamma. It's very easy because, like I said, alpha, beta, gamma. Okay, where can we find alpha, beta, gamma? If you can find a cosine alpha, cosine beta, and cosine gamma. Okay, so okay, let's write equal to the magnitude times the unit vector of the resulting force. The unit vector of the resulting force. And don't forget that in the unit vector of in the unit vector in the unit vector in the unit vector in the unit vector okay, unit vector is just the unit vector is just equal to cosine alpha I plus cosine beta j plus cosine gamma. Okay, don't forget the unit vector just the cosine alpha, cosine beta, and cosine gamma. And the problem wants you find the coordinate of the direction angles. Direction angle, that means alpha, beta, gamma. Okay, if you find the cosine alpha, cosine beta, cosine gamma, you can find alpha, beta, gamma very easily. And the cosine alpha, so what is cosine alpha? Okay, it's just the x component of a unit vector. Okay, x component of a unit vector, and y component of a unit vector, and z component of a unit vector. Okay, so so what's the x component of unit vector gamma? Okay, what's the x component of your unit vector? It's a. Okay, in this case, it's frx. It's fr. Sorry, r. It's x component divided by magnitude. Okay, and cosine beta is y component divided by magnitude. And your z component of the unit vector, the z component of the unit vector is cosine gamma. It's the this fr z r z component. Okay. Z component of a unit vector, just the component divided by the magnitude. Okay. So you can, if you with this information, you can solve this very easy. Okay. So what is FR? Okay, so we have to do some calculation. Okay, so it's 50 square plus 40 square plus 180 square, and take square root. And okay, it's 101. Okay, the unit is Newton. So what is your cosine alpha? Okay, it's 191. The denominator is always 1 or 191. So what's the numerator? Numerator, the cosine alpha, the numerator is your resultant force factor, x component of the resultant force factor, 50 minus 40 and 180. Okay, so for example, so if you use your calculator 101 and do the inverse cosine, you will get your alpha. Okay, yeah, alpha is 74.8 degree. So what's your beta? Minus 40 divided by 191, and then do an inverse cosine. Give you 102.1, 102.1 degree. So and finally, what is gamma? It's 180 divided 190. Okay, and then inverse cosine. So 18.7 degree. Okay. Okay, so its magnitude is 191 Newton, and its coordinate directional angle is 74.8 degree and 102.1 degree, and gamma is 18.7 degree. Let me check the answers. Mm, then, yeah, why the gamma? The gamma is a little different. Gamma is 19. Yeah, and the gamma is a little bit. Why? Why is that? Yeah, there is something wrong. Okay, 180. I mean, 180 divided 191 cosine. Oh, 19 point. Okay, maybe I did some. Maybe my is a little made a little mistake here. So sorry. So the gamma is 19.5 degree instead 19.5 degree. Okay. So okay, I think that's more that's more correct answer. Okay. So that's a very simple exercise. Give you a two force vector, and these two force vector are represented by Cartesian coordinate. And then find the resulting force. Add these two force vectors, component added by component. Okay, and you get your resulting force vectors. And the vector equal to magnitude times the directions. Okay, so you just fact you just factor your magnitude out, and each and the left and the terms left will be your unit vectors. And the unit vector, the x component is cosine alpha, y component is cosine beta, z component is cosine gamma. Okay, and then after you find the cosine alpha, cosine beta, and cosine gamma, you will find the alpha, beta, gamma. It's just the coordinate, the fractional angles. Okay, so okay, just the it's very simple example for 3D vector, and we'll demonstrate another example for the 3D vector again. Okay, I'm gonna start the video here. See you in next video. Bye bye.